4.3, the fundamental theorem of calculus. Like I said, if this sounds important, then it is. This fundamental. In fact, most fields of mathematics have a fundamental theorem. And this is kind of the theorem that drives a lot of what happens throughout the rest of calculus. What's the big idea of the theorem? There are two parts, but the part one is the one, or part two is the one we use like 95% of the time. And part two, I'm just barely going to mention. I usually spend a little bit more time on it, but because we're in this coronavirus stage, I'm going to breeze right past it. But what's the big idea? It says if we have an integral, so remember what this means. This means we're taking the area, but if our function in here is a derivative function, so notice this is a derivative. So if we're taking an integral of a derivative, we get back the original function just as it is. So that means that somehow this integral and this derivative are opposites of each other. They do the opposite thing of each other. And we'll talk in just a little bit about, towards the end, about why that might be the case. But for right now, let's just talk about how we can use this thing. So the way we can use it is that means that if we know an antiderivative, if I have the integral of some function, and I know the antiderivative, then all I have to do is put the antiderivative right here and plug these two numbers into my antiderivative. And so this is my antiderivative. And what we usually do is we often write a vertical line and put an A and a B. And so this is the traditional notation. And what this notation means is you plug B in and you plug A in, and then you take the difference and you subtract them from each other. So what let's do is let's just start by doing some problems, and we'll kind of see how the fundamental theorem works out. Okay, so problem number one was the integral from 0 to 4 of 1 minus x dx. And so all we have to do is say, well, what is the antiderivative of this? And it's actually not too hard, because the antiderivative of 1 is x, and the antiderivative of x is 1/2 x squared. So, so this is the antiderivative. Hopefully you've done those homeworks and you're kind of getting familiar with it. So just remember, the derivative of x is 1, the derivative of x squared is 2x, so we need the 1/2 in front of here. Okay, so this is our antiderivative, so I'm going to write it like this, and then I'm going to put that bar, and I'm going to put 0 and 4 on here. So what does that mean? That means I now just take 4 and 0 and plug them in my equation. And so I've put 4 minus 1/2 times 4 squared. That is what I get when I put 4 into my antiderivative equation. So this I could write as f of 4. And then I'll put a minus sign, and then I'll plug 0 into that. And so I've got 0 minus 1/2, 0 squared. And that is f of 0. Where this is not f, this is f prime of x, right? So this is the antiderivative. So I put 4 in my antiderivative, I put 0 in my antiderivative, and that's what we've got. And so now I'm ready to calculate this out and get the answer that will recognize, well, I don't know if we'll recognize it, but let's see. So we get 4, let's see, this is 16, 4 minus 8, so it looks like I get -4 for my answer. Negative, that seems like an odd response. Does it? Maybe it feels a little surprising to get a negative sign for your answer. But it actually makes sense if you think about it, because this problem is 1 minus x. It starts at 1, and it just is a function that has a negative slope, a slope of -1. So it's going to cross here at x equals 1, and then we'll go 1, 2, 3, 4. And so really what we're talking about is this area right here that has a height of 1 and width of 1, and then a height of 3, and it goes down to 3 because this is -3 right here. And so I could, if I wanted, I could have just done this as a geometry problem, and notice that this problem is 1 times 1 times 1/2, so this is 1/2, and this is 3 times 3, 1/2, 3 times, so this is 1/2 times 1 times 1. This one is 1/2 times 3 times 3. So this is 1/2, and this is 9/2. And so I could take, well, 1/2 is the positive part of the area, 9/2 is the negative part of the area, so I could put them together and get -8/2, which is -4. So this answer that we got over here actually matches the answer if we did this problem with geometry. So doing geometry, we can see that the area should be -4, and that's what we got using our fundamental theorem of calculus. All right, so let's jump into the next problem. The next problem is the integral of 10 minus x squared dx. We actually did this as our example problem when we were drawing rectangles at the beginning of, I think, section 4.1. And if I remember, we got like -16. We know the answer is between 16 and 24 or something. I can't remember the exact numbers. That's too bad. But we kind of had some range. I think -18 was kind of the closest estimate we came. So we should expect this answer to be in the 18, 19, 20 range when we're all done. But let's just do it and see if we get the right answer. So what am I going to do? I'm going to take the antiderivative. The antiderivative of 10 is 10x. And the antiderivative of x squared, you've got an x cubed, but you need a 1/3 in front of it. So here's my antiderivative. I'm going to put this bar with the 0 and the 3. What does that mean? It just means we put 3 in our equation. So 10 times 3 minus 1/3 times 3 cubed. That's everything with the 3 in there. Put a minus sign, open up parentheses, and put a 0 in there. 10 times 0 minus 1/3 times 0 cubed. Let's put all this together and see what we get. We get 30 minus, let's see, it looks like 9 minus 0, minus 30 minus 9, minus 0, no, so those are all 0. So 21. Okay, I was a little bit off in my estimate, 18 or 19. 21's kind of in the range that seems reasonable, though. So 21 is our area here. Okay. Finally, let's do cosine of x. And this one will be kind of interesting for us, I think. So when we do cosine of x from 0 to pi, we're going to take the antiderivative of cosine. And what is the antiderivative of cosine? Its sign, is it positive or negative? It is positive sign because the derivative of sine is positive cosine. Remember, these are backwards from what they were when we did derivatives. So we'll do sine, evaluated from 0 to pi. And so that means we get sine of pi minus sine of 0. But sine of pi is 0, and sine of 0 is 0, so we get 0 for our answer. Is that a surprise? No, we talked about this a while back, and if you remember what cosine looks like, we know that cosine of x has the basic shape that looks like this, where it starts here and comes down here. And so if I put pi right here on my graph, then the negative part and the positive part cancel each other out, and we end up getting 0 for our answer. Okay, that process that we just went through with those 3 problems is a really important process. I'm going to have you do it a bunch of times in homework. We're going to do it more times now. We're going to do it more times today before we're done. It's a really important process, and when you get to Calc 2, we're going to take these same problems, which are going to kind of make them explode. So this is kind of like, so think of it like when we first started learning the shortcut method for doing derivatives. It's like a shortcut method for finding areas, for finding these integrals. And just like we learned lots of rules, we learned the product and the quotient and the chain rule. When you get to Calc 2, you're going to learn a lot of rules to use to find these, except those rules will be a little bit more interesting, a little bit more challenging. I'm not going to go all the way through the proof, but let me just give you a little glimpse of how the proof works. So I drew this out beforehand. This is going to look overwhelming, but let me just tell you briefly how we come up with the proof of this theorem. Why is it true that this should be the case? Well, if this function is f prime of x, and I have my graph here, then what I'm going to do to find the area is I'm going to break it up into a bunch of rectangles. Well, I can actually pick any point I want on those rectangles. So what I'm going to do is I'm going to use the mean value theorem to find these points. Now, the mean value theorem we went very quickly through in class as well, but the mean value theorem says that there's a point where the derivative is the same as the slope of the secant line. So this point here has a derivative that's the same as the slope of the secant line. And so at every point, I'm going to choose that point whose derivative is the same as the slope of the secant line. And I'm going to do that in every single section that I go through. Well, if you look closely, what you'll see is that we get this, that means this, which is our height base times height, base times height, base times height. If you get this base times height, using the mean value theorem, it turns into this secant line equation times delta x, secant line equation times delta x. But what you'll notice is that each of these bottoms, this is x1 minus x0, that is this distance, which is exactly delta x itself. This part right here is that part right here, which is also exactly delta x. So what you'll see is that every delta x cancels out with the denominator, and I'm left with f of x1 minus f of x0 plus f of x2 minus f of x1 plus, and I go all the way across. And what you see is that in this first term, I have an x1, and in the second term, I have a negative x1. So this x1 and this x1 cancel each other out. This x2 and that x2, which would have been from this problem, cancel each other out. And everything cancels out except two pieces. This very first piece of this equation stays, and that very first piece of that equation is minus f of x0, and this very last piece of this equation stays, plus f of x in. Well, what does that mean? Those equations are exactly the equations we mean f of negative f of a plus f of b. Or if I like, I could write it in the traditional form, f of b minus f of a. Okay, you don't have to know the proof, but I want you to know that it's not magic. So the reason why this works, there's nothing magical going on. It's the mean value theorem. It's choosing these points so that their slopes are the same as the secant lines. That allows this entire problem to work out the way we want it to. Okay. What I want you to do right now is pause your device. So actually, I'm gonna cut it off. I'm gonna make another video that follows this one. So what I want you to do is try 4.9. Try all three of the 4.9s. And by the way, on the last one, you'll have to do a little bit of algebra first. So you can't, just like in derivatives, you can't just, when things are divided and multiplied, you can't just do everything by hand. You have to do a little bit of algebra. So do a little algebra to simplify it, and then do your integral. So try 4.9, and then after you try 4.9, come right back and watch the second video where we'll do those three problems, and then we will talk a little bit about the other version of the fundamental theorem of calculus before we're done with the section.